Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to go over the Bronsted-Lowry definition of acids and bases. So let's get into this. So what is the Bronsted-Lowry definition? Well, that was introduced in 1923 by the two scientists Bronsted and Lowry. And this is a more widely applicable definition. And the reason for that is because it focuses on the transfer of a proton or an H plus from one substance to the other, rather than focusing on whether or not this substance produces H plus or produces OH minus. So according to the Bronsted-Lowry definition of acid, an acid is merely a proton donor or an H plus donor. We call the H plus a proton because hydrogen has one electron. And so to get rid of that one, it has one proton, one electron. If you get rid of that electron, then all you're left with is the nucleus, which is a proton. So we just call it a proton instead of H plus. So you could call it either way. So we refer to the H plus ion as a proton because that's all that it is that's left is a proton. So an acid is a proton donor or H plus donor, and a base is a proton or H plus acceptor. And so here we look at a couple of examples. So here we have our HCl again. So our hydrochloric acid is a molecule. It's going to ionize into H plus and Cl minus into those ions. And so the H plus again is going to react with water. So the H plus here that's produced gets transferred to the water. So HCl becomes the proton donor. It's donating the H plus to water, and now water becomes the proton acceptor. And so it accepts the proton, and you get the hydronium ion, and you get the chloride ion that's left. So in this case here, the HCl is the acid, and water is a base according to this definition of acid and base. So water is a base because it's accepting the proton from HCl. And the next example here shows the more wide application of this definition compared to that of the Arrhenius definition that we covered in an earlier video. So according to the Arrhenius definition of a base is something that produces OH minus or hydroxide ion. And in order to do that, you would have to have the hydroxide ion as part of your formula. But here you can see for ammonia, there is no hydroxide ion in here. So according to the Arrhenius definition, it would not be a base. But according to the Bronsted-Lowry definition, it is a base. And we know that it's a base by experience. When you put the ammonia into water, we know that bases generally will turn red litmus paper blue. And when you put ammonia in water, you'll see that when you take your red litmus paper and you put it in the water, it will turn blue. So it acts as a base, but according to the Arrhenius definition, it would not be a base. But if we use the Bronsted-Lowry definition of a base, we'll notice that here we have NH3 and we have water. Here, one of the hydrogens from the water is going to be transferred to NH3, and that becomes NH4 plus, and then you get OH minus left over. So one of the hydrogens, so if you look at it this way, so we have HOH. So one of these hydrogens gets transferred to the NH3. That's going to produce NH4 plus. This is your ammonium ion, and then your hydroxide ion is left over after the transfer. So according to the Bronsted-Lowry definition, then this water is acting as an acid now because it's transferring an electron, I'm sorry, it's transferring a hydrogen or an H plus to ammonia or a proton to ammonia. So this becomes a proton donor. And so the ammonium is a base because that is becoming a proton acceptor. So in this case, it's clear that ammonia is a base. And the other thing to note here is that if we reverse this reaction and we make the NH4 plus, the ammonium, and the OH minus as reactants, we now see that the ammonium here is acting as a base, or I'm sorry, an acid. So I'll use red. So this is acting as a Bronsted-Lowry acid because it's now going to donate an H plus to OH minus, and that's going to form water. So then this OH minus is our base because the hydroxide ion is going to accept a proton or H plus from the ammonium, and that's going to form liquid water, and then we're going to get the NH4, the ammonia, left over. So now you can see here that this is the acid and this is the base that's reacting to form these products. And over here you have, this is the base and this is the acid forming these products. So here we can see a few things. One, acid and bases are always occur together. So why is that? Because you have a proton or H plus that needs to be transferred from one thing to the other. The H plus is not something that just goes away and floats around and doesn't get picked up. So in order to be picked up, there's got to be something that's going to accept it. And in order to accept a proton, there's got to be something that's going to give it. So you can't give unless there's something willing to take what you're giving. So they occur together. So acids and bases are always together in the reaction. The other thing to note is that some substances can act as both acids and bases, and we call those amphoteric substances. And here's a great example. You can see here, water in this reaction with the hydrochloric acid is acting as a base according to the Bronsted-Lowry definition because it is accepting a proton or H plus from your hydrochloric acid. But in this reaction, the water is acting as a donor, a proton donor or H plus donor to the base NH3. And so in this case, water is acting as a Bronsted-Lowry acid. And so water, therefore, is a amphoteric substance. It can act as a base or an acid depending on the reaction. And the other thing, the last thing to note is what is called a conjugate acid-base pair. And what is a conjugate acid-base pair? That is two substances that are related to each other by the transfer of H plus. And so we could see that here. So this here, this HCl is related to Cl minus by the transfer of a hydrogen. So HCl transfer a hydrogen, loses the hydrogen, and becomes Cl. You can get the HCl back by adding hydrogen to Cl, and you can get the HCl. So these two are related to each other by the transfer of a hydrogen. You get one from the other by transferring the hydrogen. So this would be your acid, and this would be the conjugate base. Why is it the conjugate base? Because if you go backwards, this will pick up the hydrogen from HCl and then reform the HCl. So, I'm sorry, from the H3O. So if we go backwards, the Cl minus, the chloride ion, is going to pick up a proton from the hydronium ion to form HCl back. So chloride ion would act as a base by acting as a proton acceptor. So it would take H from the hydronium and form that. So this would be a conjugate. This would be the acid. This would be the conjugate base. And then you can see these two here, water and H3O, these are related to each other by the transfer of a hydrogen as well. So because if I add hydrogen to water, I get the hydronium. If hydronium loses the hydrogen and transfers it somewhere else, I get the water back. So this would be the base, and this would be the conjugate acid. Same thing down here. So NH3 and NH4 plus are related to each other by the transfer of a proton. So if NH3 picks up the proton from somewhere like water, then this will form the NH3 plus. So then this is the conjugate acid of this base. Why is it the conjugate acid of this base? Because this, if we were to reverse the reaction this way, then the NH4 plus would transfer a hydrogen to OH minus to give back the NH3. So these are connected to each other. They're related to each other by the transfer of a hydrogen. Same thing for the water here. So if I have this water as an acid, then the water and the OH minus are related to each other by the transfer of hydrogen. If I transfer hydrogen to the ammonia, then I get the OH. If the OH takes a hydrogen from the ammonium, I get the water back. So if I go this way, I get the water back by the transfer of a hydrogen. So then this would be the conjugate base of this acid. So this is the base, this is the conjugate acid. This is the acid, this is the conjugate base. So that's what we mean by a conjugate acid-base pair. Now there's something I want to point out, and this is the last thing, is that when we talk about conjugate acids and bases, those are not the reactants. So whatever's on the reactant side, that's what we refer to as the acid and base, right? So when we talk about conjugate acid and bases, we're not referring to these. We never want to call these conjugate acids and bases. We want to call these the acid and base because they're on the reactant side. Whatever's on the product side, those are what we're referring to as the conjugate acid, conjugate base. So conjugate acid and conjugate base are on the product side, not on the reactant side. Acid and base are on the reactant side, not on the product side. Now, if we were to reverse this, right, then what was the conjugate acid in this one now becomes the acid in this reversed reaction because they're on the reactant side. So this is the acid in this reaction because it's the conjugate acid in the other reaction, right? So what was the conjugate base becomes the base. And then what was the acid over here becomes the conjugate base over there or over here. So this is the base. It becomes the conjugate base over here. So I'll put CB. So this becomes the conjugate base over there. And then what was the acid over here becomes the conjugate acid over there. And so all of that is because we are defining acid and base differently according to the Bronsted-Lowry definition. So I hope this was helpful. I hope you enjoyed this video and learned a lot from it. If so, please smash that like button, subscribe to my channel, hit the notification bell so you can be notified by other videos I put out. Put a comment in the comment section. Let me know what you think and if you've got any questions that you would like me to answer. Thanks for joining me and have a great day.